Hey, welcome to The Explainer. Today we're diving into a chemical that's literally born in lightning strikes and has the power to both create and, well, destroy. We're talking about nitric acid. It's got such a cool story, so let's just jump right in. So have you ever been told not to play in the first rain of the season? I know I have. And the reason isn't just about mud or dirt. It's actually because that first rain is washing the atmosphere clean of all sorts of pollutants, which creates a kind of mild acid rain. And guess what a key ingredient is? Yep, you got it. It's nitric acid, formed right there in the middle of a thunderstorm. Way back, before we called it nitric acid, the alchemists had a name for it that sounds like it's straight out of a fantasy novel. Aqua fortis. That's Latin for strong water. And why'd they call it that? Well, because this stuff could dissolve almost any metal they threw at it, which must have seemed like actual magic back then. And you know what? That incredible reactive power is still what defines it today.
Okay, so how do we get this strong water anyway? It's pretty wild, actually. It's made in two totally different ways. First, you've got the raw, chaotic power of a lightning storm. And then you've got the calm, controlled environment of a science lab. Let's start with nature's dramatic approach. Picture this, a lightning bolt flashes across the sky. The temperature in that bolt can hit an insane 3,000 degrees Celsius. That's hot enough to do something incredible. It rips apart the nitrogen molecules in the air, which are usually super stable and don't like to react. Once they're broken apart, they can finally combine with oxygen, and boom, you get nitric oxide. But it's not done yet. This stuff is unstable, so it quickly grabs even more oxygen and becomes nitrogen dioxide. Then, that gas dissolves in the tiny water droplets in the clouds, reacts with just a little more oxygen, and there you have it, nitric acid, falling down as rain.
And this is where things get really interesting. You see the contrast? Nature uses this incredible brute force, a lightning strike, to make a very weak, very dilute acid. But in the lab, it's all about finesse and control. We use very specific chemicals, we control the heat perfectly, and we get a much more concentrated acid as a result. It's a classic case of scientists looking at what nature does and thinking, okay, we can do that, but let's make it a little more efficient.
Now, making this stuff in a lab isn't something you just wing. There are some serious rules. For instance, why does everything have to be made of glass? Well, those acid fumes are no joke. They're so corrosive they literally eat through a rubber or cork stopper. Then there's the heat. You've got to keep it below 200 degrees Celsius. Go any hotter, and you could crack your glassware, or worse, you start breaking down the very nitric acid you're trying to make. And the last big rule? You have to use concentrated sulfuric acid. Why? Because it's non-volatile. It doesn't turn into a gas easily, so it won't mix in and contaminate the pure nitric acid you're producing.
Okay, so you've done everything right, followed all the steps. But when you look at your final product, the nitric acid is kind of yellow. What's up with that? Well, pure nitric acid is actually perfectly colorless. The problem is, it's just a little bit unstable. So even at room temperature, a tiny bit of it breaks down. And when it breaks down, it creates water, oxygen, and remember that reddish-brown gas we talked about? Nitrogen dioxide. That gas then dissolves right back into the acid, and that's what gives it that classic yellowish color.
All right, let's talk about nitric acid's superpower. Its defining personality trait, really. It's not just that it's an acid. Lots of things are acids. The real key here is that it's a crazy powerful oxidizing agent. Now, that's just a fancy way of saying it is extremely good at shoving oxygen onto other things, and that's what makes it so incredibly reactive. And this whole oxidizing thing is why it doesn't play by the normal acid rules. You see, when most acids react with a metal, you get bubbles of hydrogen gas. Simple enough? But nitric acid, nope. It's so good at reacting that it can attack metals that other acids just can't touch. Really, only the noble metals, the super unreactive ones like gold and platinum, are safe from it. A really great way to see this power firsthand is to drop a piece of copper into it. And this is where it gets really cool, because the outcome of the reaction changes completely depending on just one little thing: how concentrated the acid is. Okay, check this out. If you react copper with dilute, watery nitric acid, you'll get nitric oxide, which is a colorless gas. But if you use the strong stuff, the concentrated nitric acid, you get a totally different gas, that reddish-brown nitrogen dioxide. Now, in both cases, you'll end up with a pretty blue solution of copper nitrate, but the gas that's produced, that's the dead giveaway. It tells you exactly which concentration you were using. So here's the big takeaway, the thing to remember. If you're ever in a lab and you see those telltale reddish-brown fumes bubbling off a reaction with a metal, your brain should immediately go, concentrated nitric acid.
It's seriously one of the most classic, unmistakable visual clues you can get in chemistry. Okay, so we've got a good handle on how this acid behaves, but how do you prove that what you have is actually nitric acid? And on the flip side, how do you go from making a tiny bit in a beaker to making enough to, say, fertilize entire farms?
The trick to identifying nitric acid, or any of its related salts, is to look for its chemical signature, which is something called the nitrate ion. And luckily for us, chemists have this really famous, super specific, and honestly, just a really cool-looking test to find it.
It's called the brown ring test. So imagine you're doing this. First, you take your mystery solution and you add a little bit of freshly made iron-2 sulfate. Next, you tilt the test tube and, very carefully, you let some concentrated sulfuric acid slowly trickle down the inside. Since the acid is heavier, it sinks right to the bottom and makes a clean layer underneath your solution.
And then you watch. Right at the junction where the two liquids touch, this amazing brown ring will appear if you have a nitrate. It's this unstable little compound that doesn't last long, but it's the positive sign you're looking for. But, and this is a huge but, the iron sulfate you use has to be freshly prepared. Seriously, if it's been sitting around for a while, it will have already reacted with oxygen from the air, and the whole test just won't work.
So the brown ring test is fantastic for figuring out what's in a test tube. But what about when you need, like, thousands of liters of this stuff for making fertilizers or even explosives? Yeah, that little lab recipe is not going to cut it. We have to scale things up, way up. And that's where something called the Oswald process takes over. This is the industrial workhorse, the powerhouse method for cranking out nitric acid. Basically, you take ammonia and air and you blast them over a super hot platinum catalyst. We're talking around 800 degrees Celsius. It's an incredibly efficient process that lets us turn cheap and abundant ammonia into tons and tons of valuable nitric acid.
And all of this brings us right back to where we started, to nitric acid's two-sided nature. On one hand, because of processes like Ostwald's, it's a key ingredient in fertilizers that literally help feed the planet. It's a creator of life. But on the other hand, that same strong water reactivity makes it a crucial part of explosives and a cause of corrosive acid rain, a destroyer. So what is it, a creator or a destroyer? I think the answer, like with so many things in science, is that the chemical itself is neither. Its true nature really just depends on what we decide to do with it.